Let us start chapter 5 module 12. In this module we shall discuss a very well known theorem which is called Stone-Weierstrass theorem. In fact, if we consider the space C close interval AB, that is the space of all real valued continuous functions defined on the closed interval AB, then we know that set of all polynomials is dense in this space. Here the topology is the soup metric topology. We can also take the space of all complex valued continuous functions. But what happens if we wish to generalize this thing in case of arbitrary topological spaces? Because there does not exist any polynomial. In the Stone-Weierstrass theorem, we shall generalize this theorem for arbitrary compact spaces. So, let us come in the slide presentation. So, I have already mentioned that set of all polynomials in the space CAB, where CAB means the set of all real or complex valued continuous functions defined on the closed interval AB is dense. In this way, we can also prove that CAB is separable. In fact, if we take of all polynomials with rational coefficients, then that becomes a countable collection and therefore CAB becomes separable. Now, if we wish to replace the closed interval AB by a topological space or by some compact Hausdorff space X, then the basic problem is how we shall replace the polynomial, because for arbitrary topological space there is no notion of polynomial. But we can resolve this. To resolve this, let us consider two functions 1 and x defined on the closed interval AB. 1 means the function from closed interval AB to C, where 1 of r is equal to real value 1 for any r belongs to closed interval AB, and x is the identity mapping. Now, this set of all polynomials, if we denote it by script p, is identical with the set of all functions which can be built from these two functions 1 and x by following three operations: multiplication, multiplication by real numbers, and addition. In fact, script p is an algebra of real functions on closed interval AB, for it is closed with respect to these three operations. Even more, it is a sub-algebra of CAB. We say that script P is a sub-algebra of CAB generated by 1 and x, for it is a sub-algebra containing 1 and x which is contained in every sub-algebra with this property. Now, let us consider closure of P as the closed subalgebra of CAB generated by 1 and x. As above, this means that closure of P is a closed subalgebra containing 1 and x, which is contained in every closed subalgebra. To prove our main theorem, we need some preliminary properties. In fact, we have to consider the subalgebra structure in C of x. We also want some lattice structure in Cx, where x has considered as compact Hausdorff spaces. If f and g are two functions in Cxr, we recall that their join and meet are defined as f join g is equal to maximum of fx and gx, and f meet g is equal to minimum of fx and gx. This is a known fact that both f meet g and f join g are continuous functions. That means both f join g and f meet g are in Cxr. Our first lemma states that condition which guarantees that a closed sublattice of Cxr is equal to Cxr. Here we recall that a partially ordered set will be called lattice if it contains join and meet of any two points. So, Cxr is of course a lattice, and we also know that Cxr is an algebra. So, Cxr is a lattice ordered algebra. Let capital X be a compact Hausdorff space with at least 2 points, and let capital L be a closed sublattice of Cxr with the following property: if x and y are distinct points of capital X and a, b are any two real numbers, then there exists a function f belongs to L such that fx is equal to a and fy is equal to b, then L equals to Cxr. In fact, this given condition is known as separating points. That means if x and y are two distinct points in capital X, then there exists some function in capital L such that fx not equal to fy. So, this lemma says that if L be a closed sublattice which separate points, then L is equal to Cxr. For the proof, let epsilon be a positive real number. Since L is closed, it suffices to construct a function g in L such that gx lies in between fx minus epsilon and fx plus epsilon for any x belongs to capital X. In fact, then f being limit point enters in capital L as L is closed. Now, let x be a point in capital X be fixed and let y be a point different from x. then there exists some function fy in capital L such that fy of x is equal to f of x and fy of y is equal to f of y. Now, for each y, let us consider the open set gy is equal to all x such that fy x less than fx plus epsilon. Then for each y, gy contains both x and y. Therefore, the collection gy such that y belongs to x where y not equal to x is an open cover of x. But since x is compact, this open cover has a finite subcover which let us denote by g1, g2, gk. Now, if corresponding functions in capital L are denoted by f1, f2, fk, then gx is equal to f1 meet f2 meet up to meet fk is a function in capital L such that gx of x is equal to fx and gx of z strictly less than fz plus epsilon for all points z in capital X. Next, consider the open set Hx is equal to all z such that gxz greater than fz minus epsilon. Now, we have that x is in Hx for any x. Then again the collection Hx such that x belongs to capital X is an open cover of capital X, and therefore by compactness of x we have a finite subcover, say H1, H2, HL, which covers x. We denote the corresponding functions in capital L by g1, g2, gl, and let us define g by g1 union g2 union up to gl. Here union and join are equivalent. Clearly, g is a function in L with the property that gx is in between fx plus epsilon and fx minus epsilon, which holds for all x in X. This completes our proof. Next, we shall use absolute value of a function. We observed that the lattice operation in CXR are also expressible in terms of addition, scalar multiplication and the formation of absolute values. One can easily verify that f join g is equal to f plus g plus modulus of f minus g by 2 and f mid g is equal to f plus g minus modulus of f minus g by 2. So, if a subalgebra has the property that f belongs to that subalgebra implies modulus of f belongs to that subalgebra, then that subalgebra should be closed under the formation of joining and meet. Lemma: let capital X be an arbitrary topological space, then every closed subalgebra of CXR is a closed sublattice of CXR. As I have already told, we need to show that if f is in a subalgebra, then modulus of f is also in that subalgebra. To prove this, let script A be a closed subalgebra of CXR. Therefore, we wish to prove that if f is in script A, then modulus value of f is also in script F. Now, since f is a continuous function on a compact space F, then f must be bounded. There exist constants a and b such that f less or equal to b, greater or equal to a. Now, by Weierstrass approximation theorem, for any positive number epsilon, there exists a polynomial, say px, such that modulus of px minus modulus of x less or equal to epsilon when x is in the closed interval ab. Now let us define g from x to r by gx is equal to p of f of x. Since script A is an algebra, g also is in script A. For all x belongs to capital X, we have modulus of g of x minus modulus of fx, total modulus, less or equal to epsilon. Since script A is closed under the uniform convergency topology, this implies that modulus of f is in script A. Therefore, script A is a closed sublattice of CXR. Now we are in a position to prove the real Stone-Weierstrass theorem. Let capital X be a compact Hausdorff space and script A be a closed subalgebra of CXR which separates points and contains non-zero constant functions. That means all constant functions 1, 2, 3, every real number are in script A. Then script A equals CXR. If capital X has only one point, then CXR contains only constant functions, and since script A contains a non-zero constant function and it is an algebra, it contains all constant functions and equals CXR. So we assume that capital X contains more than one point. Now by the above lemma, it is sufficient to show that if x and y are distinct points of capital X and if a and b are any two real numbers, then there exists a function f in script A such that fx is equal to a and f of y is equal to b. Since script A separates points, there exists a function g in script A such that gx not equal to gy. If we now define f by the formula f of z is equal to a into gz minus gy by gx minus gy plus b into gz minus gx by gy minus gx, then f clearly has the required properties. Thus, we have been able to prove the real Stone-Weierstrass theorem. So, we have proved here real Stone-Weierstrass theorem, which says that if script A is a closed subalgebra of Cxr which contains all the constant functions and which separates points, then script A is equal to Cxr. Then it is natural to ask whether the same kind of theorem holds for Cxc, that means for the space of all complex valued continuous functions defined on a compact Hausdorff space capital X. Let us see it in the presentation. So, we shall examine here that whether real Stone-Weierstrass theorem can be generalized for complex valued functions also. Let us examine the following example. Consider X as the closed unit disk in the complex plane. Now, also consider this set script A of all functions in Cxc which are analytic in the interior of capital X. Then script A is clearly a subalgebra of Cxc and one sees that it is closed by using Morera's theorem. Script A also separates points, for it contains the function f defined by fz is equal to z. Script f also contains all constant functions. In spite of this, script f does not equal to Cxc, for the function g defined by gz is equal to g bar is not analytic. So, in what case we can extend the real Stone-Weierstrass theorem in case of complex valued functions? For this, we need with little bit more hypothesis. It will also be convenient for us to define the real part and imaginary part of a function f. We define real part of a function f as f plus f conjugate by 2 and imaginary part of f as f minus conjugate of f by 2, where conjugate of f is defined as f bar of x is equal to f x bar. If a complex function f has different values at two distinct points z, then at least one of the functions rf and if also has different values at these points. It will be helpful for us. Now, let us come to the proof of complex Stone-Weierstrass theorem. This says as the following: let X be a compact Hausdorff space and let script A be a closed subalgebra of Cxc which separates points and contains a non-zero constant function and contains the conjugate of each of its functions. Then script A is equal with Cxc. That means here the conjugate condition is the extra hypothesis. To prove the complex Stone-Weierstrass theorem, we shall use the real Stone-Weierstrass theorem. The real valued functions in script A clearly forms a closed subalgebra script B of CXR. First, we shall show that script B is equal with CXR. We begin by showing that script B separates points. Let x and y be distinct points in capital X. Since script A separates points, there exists a function f in script A which has different values at x and y. Since, as we have mentioned, that if f separates points, then at least one of Rf and If has different values at x and y. That means at least one of Rf and If separates points. Now, since script A is an algebra which contains the conjugate of each of its functions, both Rf and If are in B. So, script B separates points. We next show that script B contains a non-zero constant function. By our hypothesis, script A contains some non-zero constant function g. Since script A is an algebra which contains the conjugate of each functions, that is, script A is closed under the formulation of conjugation, we have g product g bar is equal to modulus of g square is a non-zero constant function in script B. Hence, applying real Stone-Weierstrass theorem, we have that script B is equal with CXR. Now, to complete the proof of complex Stone-Weierstrass theorem, let f be an arbitrary function in CXC, then Rf and If are in CXR and are thus in script B. But since f is equal to Rf plus I into I of f and script A is an algebra, f is in script A and thus script A is equal with CXC. This completes the proof of complex Stone-Weierstrass theorem. Therefore, in this module, we have discussed about Stone-Weierstrass theorem. First, we have proved the real Stone-Weierstrass theorem, which says that a subalgebra script A of CXR with some conditions is equal with CXR for any compact Hausdorff space X. Next, we have used this theorem to prove the complex Stone-Weierstrass theorem. We have required only the case that script A will be also closed under the formation of conjugation. With this, we have been also able to prove the complex Stone-Weierstrass theorem. With this, we end this module. Let us pass to the next module.